Hello, my name is Isabella, and I will be your host for another mathematics video brought to you by RJ. My question for you today is, can we approximate the sum of cosines of the harmonics? You might be asking, what is a harmonic? A harmonic is a reciprocal of a natural number. This is the harmonic sequence. This is a harmonic number, the sum of harmonics from 1 to n. Unfortunately, as of yet, there is no closed formula for a harmonic number. But suppose we place the harmonics inside of cosines. Is there a closed formula for this? If not, how close can we get a closed formula? This is the first quadrant of the unit circle. Now, I'm going to draw lines from the origin to the point on the circle with the appropriate harmonic angle, in increasing order. As you can see, as we go further along the harmonic sequence, the lines get closer and closer to the x-axis. Furthermore, the projection of each line onto the x-axis gets closer and closer to 1. But since we cannot divide by infinity, a projection never equal 1. Let f be a single term in this summation. Then we know two things. Each f of n is in the interval 0, 1, not including 1. And f of n is an increasing sequence. What can we deduce from these? My hand represents 1. Let each f of n be right up against 1. Now, let's look at the sequence in reverse, which means it is decreasing. Then, each f of n moves further away from 1. And since the lower bound of each f of n is 0, then the partial sum of f is in the interval n minus 1, and not including n. Let's look at f1. It has a certain value between 0 and 1, which implies it has the same value within the next integer interval mod the integers. It's stated that each f of n is less than 1, and we know the difference between any two integers is 1. Therefore, if we add f of 2 to f of 1, the sum is less than f of 1 mod the integers. Likewise, if we add f of 3 to that, the sum is less than f of 1 plus f of 2 mod the integers. The pattern continues. This tells us that the limit of the decimal part of the partial sum of f as n goes to infinity equals 0. We'll see why this is important in a moment. Let's now look at the relationship between these two statements. This states that each f of n is in the interval 0, 1, not including 1. But if we multiply 1 by n, we get n. Furthermore, the difference between 0 and 1 is 1. And the difference between n minus 1 and n is also 1. This means that, as before, there exists one f of n in each integer interval. Thus, we obtain our approximation. Simple calculation when n is greater than 1 shows that these are not equal. So how good is this approximation? We stated that the projections are an increasing sequence with a limit of 1, but never equaling 1. If we multiply each projection by n, then the limit is n, but never equaling n. This tells us that the limit of the decimal parts of our function as n goes to infinity equals 1. The difference between these two limits is less than 1, since 1 can never be included. So, our approximation is good as within an integer interval. Can we turn this into an equality? Yes, we can, by placing the functions on each side inside floor bars. Now, we have a closed formula for the approximation of the sum of cosines of the harmonics. Assuming we are only concerned with integer values, I'll leave you with one question. Can we extend this approximation to higher powers of cosines? I hope you enjoyed the video. If you did and would like to see future videos, please like and subscribe. Also, leave a comment telling RJ which areas of math you find interesting. Thank you for watching.